I did an interview recently. Interview. No, I was on a podcast recently, and I forgot to. I was. It was streamed on Twitch, but I forgot to turn off the Twitch volume. So in my headphones, I would get the question from the person asking me questions, and then repeated the question like 5 seconds later. So I was like, yes.
That's really confusing.
Yeah. But yeah, so we are live. I unlocked Hyperscape emotes. I'm not entirely sure what that means, but I keep unlocking things.
It's wonderful.
Yeah, I don't know. How are you all? Noreen is here. Awesome. We're great, Noreen. We are super hyped for this exciting stream. Okay, let's try this again. We're super hyped for this exciting stream.
Super hyped.
Awesome. So today, this is how this happened. So I have been reading a book. This book. It's called, well, you can't really read it. 7 Languages in 7 Weeks. It's a programming book, and I'm trying to read more programming books. Not just buy, but read them from start to end. It is a good exercise. So this book is, so the premise is that it gives you an introduction to 7 different languages in 7 different weeks. It doesn't matter weeks, but 7 languages, and they start from very object-oriented, and then in the middle is Scala, and then they pivot towards functional programming, and the last language in the series is Haskell. And I found the Haskell chapter the most challenging, and I said to Neil that Haskell is stupid. No, I didn't say that, but I said I have no idea from this book about what Haskell does, or why it does it, or how, or should I pay attention to it, or should I learn it a bit better, or anything. So I just, like, the book I kind of gave up. I really tried, but I didn't get anything from it. It could be also the fact that this book is aimed more towards slightly more experienced developers. So maybe, like, if you have that sort of experience under your belt, it's easier. But for me, it just was. I just thought it was unnecessarily complicated. Like, I think a person that understands the topic really well should be able to explain it in lay person's terms, and that's why Neil is here today.
Oh, okay, thanks.
to explain this crazily complicated Haskell.
Yeah.
No, as in, no pressure. We're just gonna have a conversation. I have a couple of questions. And then Neil will try his best to answer them. And then also we will do a bit of, like, a tiny demo of how to run Haskell on your own machine. And that's that. For people that have not been on this stream before, Neil has been featured previously in a GitHub topic. It was really well received. People were screaming to get Neil back on the program, and that's why we got Neil back on the program. But for those people that weren't there the last time, Neil, could you just briefly introduce yourself?
So my name's Neil Smith. The day job is I'm a lecturer in computing at the Open University in the UK. So my interests are a lot about data science and machine learning and things like that. I also do some outreach work with the university, and also looking at how to teach programming, especially to beginners. And my sort of guilty little secret is that actually it's my natural way of thinking about programming is much more along the functional programming side of how to do these, rather than the more procedural stuff that you get with Python and JavaScript and things. So every once in a while I get some free time, I can go off into my little corner and write some Haskell and have lots of fun with it, rather than having to sully myself with Python and stuff. So
that is very loaded language I'm hearing here.
But yes, of course, it's massively loaded. Yeah,
but like there is I did observe there is still this kind of gap, like I don't know, people like to throw terminology out there and like say I'm like this. Oh, someone is there's an alarm, do not be worried, it's fine. Like people like to throw things into like categories and also I guess express their expertise by throwing terms around, and there seems to be this rift of object-oriented and functional programming, or which one's better and what do you know, and even you said like it's your guilty little pleasure.
Yes.
So why do you think you have to hide that you like Haskell?
Well, I don't. It's just that so most of the stuff I do, day-to-day things, I tend to use Python most of the time, mainly because that's what everybody else is using, and there's lots of support for it, there's lots of libraries, and there's lots of, there's a large community around it, it's really good. And so that means you can be very productive in Python. But there's sort of a different part of me which has this idea that there's a very sort of pure approach to looking at problems, which comes from the functional programming side, which is quite different from how you look at problems when you're doing things procedurally. And it's nice to have that different perspective once in a while, and it's nice to just keep thinking about things in different ways. So I mean, the key thing about object-oriented and procedural programming is it has this idea of state, that things change over time and you update stuff. So you just assign a new value to a variable. And objects have their state inside them, and you have getters and setters, and you set things in the object and it changes, and then you can get that value back and things over time. And that's great for some kinds of approaches, but as we're starting to see, especially with larger systems where you've got lots of different processes interacting with each other, when you start having state that changes over time and is shared between them, you get into a mess of, hang on, last time I tried this, it did this, but now it's doing this instead. What's different? What's going on? And how do I reason about these different things interacting with each other? And so as one advantage of functional programming is that because there is no state, nothing changes, every time you call a function, if you give it the same arguments, you always get back the same result. And it doesn't matter what else is going on or what happened later. So that makes it much easier to think about these systems, or can do in some cases, because you haven't got to worry about things interacting with each other, just because there's some shared global variables or something. If they are interacting with each other, then they're doing so in a mechanism that's very clear and explained. And you can say, oh, this is the bit where they're interacting, but these other bits over here and over here, there's no interactions at all, so I don't have to worry about the rest of the system. I can keep all the complexity in one place, and then it's only there.
Okay. And so I think I liked how you, in your explanation, you completely avoided using the word immutability, which is like,
yeah.
Like this is like people would say, oh, and it has immutability or something, like, okay,
yeah,
why don't you just explain first what that means, and then okay, we can add on this sexy term for my crossword puzzles or whatever. But that's so yeah. But when you say it's a pure functional programming language, how is that different from just like, can you be a dirty functional programming language? Like what does pure mean?
There's lots of impure ones. I mean, so there are lots of ideas and techniques that started in functional programming and then have made their way into most other languages. So JavaScript has quite a few functional programming features in it. you can very easily write things in JavaScript that will take some data, and all they'll do is the data that's been given, and they'll do a transformation on it and produce some output, and you can string those together and all that kind of stuff. That's all the functional programming approach. But at the same time, you also have the idea of immutable state in JavaScript. You can update variables, you can do that as well. So JavaScript is an impure language in that sense, because it's got elements of functional programming, the elements of object-oriented programming, everything. Now, there's nothing at all wrong with that. In fact, that's quite good and powerful, because you can pick up the techniques that are appropriate for the task you've got at hand. But things like Haskell originally started as a vehicle for research into programming languages. So it has this ethos of, let's be pure, let's do everything the purest possible way, because that's useful for the academic research. And then later on, as it's come through, the ideas and some of the languages moved out into wider acceptance and into industry and places and things like that. But that's not really what Haskell was created for.
Yeah, like people say.
So it's pure in that sense because it's pure for an academic reason, not for a pragmatic reason.
And would you say, because it does, maybe because of its beginnings, has this reputation that it is a bit stuck in academia, and that yes, it's a good kind of theoretical experiment to show that this can work and you can use it. But do you see Haskell being like applied to real world cases on a larger scale, not just like in a, is it more that it fits specific cases and for there it's gold and you should use it? Or do you think it could be like a more popular language in the future?
Yeah, I mean, it is. Haskell is getting more popular. It is being used in the real world, in industry, and things are being built with it. It's got a lot of, it's got a large community around it. It's got a large standard library that can work with things. Performance is amazing with it, or can be. So it's a compiled language. It can be pretty much as fast as most other compiled languages. So close to C++ and C and things. It's sort of that order. So performance is excellent. So there's loads of stuff going on with it. The community isn't as big as some languages like JavaScript and Python, because it hasn't been adopted in that same way by large organizations. Because JavaScript is popular because it's in browsers.
Yeah.
Python got popular when Google decided to start using it and push it out. So if something big comes along and everyone goes, wow, we need to do X thing, and it's implemented in Haskell, then Haskell will take off as well. But yeah, it's not the biggest of languages. But even if you don't use it day to day, I think it's important. It's not important. It can be interesting and useful to look at it to see what you can learn from it.
Definitely, yeah, and that's what I wanted to get from it. So in this exercise that we had of having, like diving slightly into the syntax and just understanding why, because like oftentimes like a language was invented for a specific use, right? Like we have this huge project and we're using all these different solutions, but nothing really works. But we are big enough of a team, and our project is certainly deserving enough for us to go and invent or adapt a solution for it. And then from then on, like it would kind of spread out. From a learner standpoint, do you think Haskell is approachable or semi-approachable or not very approachable?
I think it's very approachable. It's very easy to get started with. The problem is quite different. And so if you started your programming career by looking at procedural languages, then when you come across something which is pure and functional, it can be a bit odd. As you had the reaction yourself, is what's going on? How do I do this? How does this work? Why am I bothered? But there's an element of you just have to kind of accept that it's different, and just in the same way that it was difficult to get the concepts of procedural programming, it can be difficult to get the first concepts of functional programming. But there's no reason why you can't start that way. It's just as approachable as anything else. If anything, quite often it's cleaner. It's easier to understand because there's less of it in the core. And then you can bolt on extra bits as you want to, and as you can explore the language, you can do more bits with it.
I just think that as a beginner, as like a junior developer, you kind of appreciate more verbose stuff. So like you want like in the beginning, I would like to write everything down and like, okay, this is like a book. You start in the beginning, and as you go down, things are executed, and it finishes at the bottom, and ta-da, and it all makes sense, right? And then when you're more experienced, you abstract more. But with functional programming, it seems that like the abstraction happens much faster. Like it's like suddenly, so you write a couple of functions, and then like they can consume each other, and like everything is like, it feels like it happens really fast. And I think, like for me, I'm happy that I started with JavaScript, or I guess Python would be a good, and they have a reputation, right, of being a more beginner-friendly languages in terms of how verbose they are, but also in numbers of resources and the community and everything like that. I think it's quite scary, the functional programming. Like it sounds clever, it looks clever. Sometimes I see something, it's like, this is so neat. It's really nice. And like you don't have to write a lot of code, and it just does it. So that's cute. And also like, because we did a closure before Haskell, and closure has all these brackets, and I really don't like that. There's so many brackets. And I appreciate that Haskell is just like, is much cleaner in that sense. Do you know anything about Golang?
No, not really.
Okay, so already, I think Attila is also, no pressure, but Attila is also watching. So he's helping with the answer there. Okay, so do you want us to try and do like a hello world type of in Haskell? Would that make sense? Like to maybe see how we can run it?
Yeah, okay. I need to start sharing the screen, don't I?
That would be beneficial, I think.
Okay, so let me try sharing a screen. Let's try. Is that working?
Yes, that is working.
Okay. Is there enough bits underneath?
Yeah.
Is this fit the screen?
Yeah, it's fitting, yes.
Yeah, okay. So, so I'm just starting the interactive console stack. You know, in JavaScript, you start the console and you start typing stuff. In JavaScript and in Python, you can do that. This is Haskell running over here. I want to print.
So to run it, you did, because the HCI, I already recognize that. That's the Glasgow
Haskell compiler. Yeah.
Right.
Okay, that's hello world.
Put string, and then
put string with a new line at the end of it. Hello world.
Oh, and if you just do, can you just do put string without line?
I don't know actually. I tend not to. Yeah, there you go.
Oh, interesting.
And there's no new line on it.
So these are all just functions that are just there, like console log.
They're built in the same way that print or console log is around in JavaScript. Then that's built into Haskell. So that's easy.
Right, but how did you? I assume that Haskell doesn't just come in every computer. How do you get to have this?
Okay, there's so wherever you install software yourself anyway, you install software in Haskell. It comes as a sort of a package thing called stack. So you may want to look for Haskell stack. At least that's how I installed it on my machine, which installs Haskell and the compiler for it and everything else. And it also has the libraries, and it also is its own package management system. So much the same way you've got things like Yarn and Gulp that do package management in JavaScript. You said yes?
Yes.
So,
yes.
Yeah. Stack is the equivalent of Haskell.
Okay. It's like the App Store for Haskell.
Yeah, exactly.
Yeah, and I saw that I use Brew for that.
Yeah.
So yeah, there's Brew Haskell stack. Someone is asking about what IDE is that. I think you have Sublime.
This is Sublime Text, yeah.
And then that's integrated terminal. Is that?
Yeah.
Yeah. Okay.
Yeah. There's an add-on package you can add to Sublime, which gives me a terminal. But it's just easy to keep stuff here for this sort of little demo. But it's completely agnostic as to whatever editor or IDE you want to use.
Okay.
Doesn't matter.
Cool.
And then the command I used, which was to start it, was up here. So stack is ask stack to do something. GHCI is the interactive Haskell environment. And I got a file here or module called main already, which is the standard one you start with. And so open up and load that.
Oh, so
on this side.
Sorry, because your face is on the top right corner. So what I can see is CK. Oh, okay. So it's stack G. Okay. I was like, why did you write CK GH?
Yeah.
Okay. So stack GH. Okay. And main is the name of the what?
It's the
name of the module.
By default, the module you start running is called main. So everything is in a module, and main is just the default one. So it's not doing anything clever. Okay. Okay.
Cool. So how do you know which functions there are? Like, because like
how do you know what's built into JavaScript?
Yeah,
you learn a bit. You look at the documentation.
Yeah, but it seems like there's like a limited number of things. So. And there's, I do quite often have to look up stuff, but it just feels like there's not so many functions. Like most of the functions are written by me or someone else in the team. Like they're not part of the existing library. Yeah.
So, I mean, so this on this side is a small sort of some bits of some Haskell I started writing, and then sort of this is a starting place for doing a couple of sort of demos of things. So I've defined a bunch of functions in here. So I've defined this function called map tree. I've defined a couple of trees to look at in a minute. And there's a function called main, which is sort of the main starting point for entry into this, into any program. You start running main. What's it called in C? The first function, the first procedure gets called. It's called main, isn't it?
Yeah, something public void,
something like
something.
That. Yeah. So that's the Haskell equivalent.
What is with the double semicolon thing?
This is a type declaration. So, for instance, with this one, I'm saying that I'm declaring something called names, and it is a list of strings.
Okay.
And look, here is a list of strings that are names.
Yay.
Okay. It's not, in that sense, it's not a complicated thing.
And it's an array, or a list, or what did you? A list.
It's a list. Haskell has lists. It doesn't generally do arrays. But there is a library that does them if you want to do them. Then you can include that, and I probably have, because in the same way, do you have a gulp file or a yarn file in JavaScript or something to say which packages you're using in a project? Yes, then I have a package file here.
Oh, like a package JSON, yeah.
Yes, exactly. So if you have package JSON, I've got package YAML, and this is just telling me that I'm actually using a library that has some containers, so trees and lists and arrays and things. That's a library I'm using. Okay.
Yeah. So.
Yep.
Okay. Can you just go to the top? Top.
Yeah.
So,
I mean, this is nothing like pretty, so don't worry.
I do not know how to judge pretty Haskell code from pretty.
Even by my standards, this is a mess. So.
Okay. So model main where? What's with the first line?
So I'm defining a module called main.
Yeah.
And this is the contents of it. This is the rest of the file. That's just the way you define packages.
Oh, okay.
And here I'm importing a couple of libraries. So I'm doing one which has some more utilities about lists. I'm importing one that knows about trees. But I'm calling that DT inside here.
Right.
So rather than typing out the full package name every time, I can just use this abbreviation.
Makes sense.
Yeah,
because list comprehension is a big thing in Haskell, right?
Yeah, can be, yes.
So what is list comprehension?
Okay, a list comprehension. So I've got a list of names, yes?
Correct.
Okay. And let's say I want to do something with each of these names, and there's a way of doing it. So if I take, so there's a function which is written as 2 pluses. So so that concatenates strings. Okay?
Yeah.
That's simple enough. If I want to add something to each of these names, then I can say add some angle brackets to the end of a name. So that says for each for each n in names, I will do this with it. And the answer is, oh, look, 3 items, each of which has those chevrons added to the end of them. Okay.
So you read kind of from right to left, like if you were coming from a like a JavaScript world where you would say for each item in this array, do this. Yes. And you can just pipe more stuff to it. Like could you do more? Like so let's say the last one is kind of your input, as in the array.
Yeah. So this is I'm taking things out of this list, and I'm doing this to each item in turn.
But could you do more? As in, could you do like another
thing?
Yeah, could you, I don't know, add a letter A as well? As in, like, could you pipe another function to it?
Let's show you something different.
Those are good names, though.
Or I can ask for the length of all of those things. Okay. I
mean, I can see how it works, but it's very unintuitive.
You get used to it. You get used to reading them.
Because it feels like you first have to decide what you want to do, and then at the end you decide who you will do it to.
Yeah, I mean the notation is inspired by a weird bit of abstract maths, which obviously the first people who were designing Haskell thought was obvious. But
Yeah.
list comprehensions,
Yeah.
they're in Python as well.
Yeah.
And I used them a lot for doing things with Python. Yeah, so it's a slightly weird notation when you first see it, but it's a very, as you're saying, it's a thing with Haskell, it's a very succinct notation.
Yeah.
If what I'm doing is manipulating things with lists, that's a very clean and quick and easy way to describe it. There's not I haven't got to start writing for this and next and beginning and end loops and things. So, I mean, the other.
Speaking of Python, is list comprehension in Haskell memory as intensive as it is in Python?
Memory intensiveness is an interesting question in Haskell.
I will let you
ponder. One of the nice things,
yes.
One of the good things about Haskell is it's a lazy language. It doesn't actually do any work until the last minute before it can get away with not doing it.
Okay, that was one of my questions. Yeah. What does that mean? Like, wouldn't you just normally you call a program or a function when you call it, and you expect it to be executed upon you calling it. But I would be a bit miffed if I call a function and it's kind of not doing it. So what do you mean by lazy doing it? And how is that good?
Do anything until you use the output of it. And it will generate the output when it's needed. It won't do it before that. So the other question is, why am I micromanaging the machine to tell it exactly what order to do things in when the machine can work that out for itself? I just say what I want. This is the answer I want. You work out the details of how to get there. That's your problem. That's the machine's problem.
Right.
I don't care. Organize your work however you want to. Just give me the results I'm asking for.
And how does that work, like in asynchronous code? Because like it makes sense that you have this code and then you say, give me all the names with the exclamation mark added to the end, and it's like, I will calculate this now, ta-tam. But what if you're like, if you can't really say, oh, it's not just a matter of computing, right? It's not like I need to run this function compute, but it's like fetching stuff, querying. Like, how does that work? Because you don't know how long it's going to take.
Well, it's the same in JavaScript where you have async functions and promises and stuff, isn't it?
Yes, true.
Yeah.
But
so if there's stuff outside that I don't know how long it's going to take, then I've just got to cope with it. However I do it. If it's stuff inside, then I just make sure that I use the information where it needs to be used. So you have the results used when they need to be used.
Okay.
I'm just specifying what the outcome has to be. Which means that so if you've got large lists of things, so if anything, if you've got a large amount of data you hold in memory, then you hold it in memory and you've got to worry about it. But you don't necessarily, however you're doing, if you're doing list comprehensions or anything else, you don't have to generate all the results if they're never needed.
Right.
So there's one example is there's a programming benchmark site where it says performance of various programming languages, and there's one which is this big hairy matrix computation, and the Haskell solution is really, really fast because they do this big hairy matrix computation and then never generate the output for it. They never produce the output anyway. So the C programs and Python programs, everything, read in the data, do the matrix computations, and then throw away the result. The Haskell program says, you're never asking me for the result of this. I'm not going to bother. Right. So it's incredibly fast because it realizes it doesn't need to do anything. So it doesn't.
Okay. So that's where the performance gain comes about. Like, only do the work when it's actually needed.
Only do the work that's easy, and also it's a compiled language, so the code that's generated by the compiler is very close to the machine, but I don't need to worry about it. And the optimizations that happen in the compiler are incredibly powerful. So the code I write doesn't look very much like the code the machine ends up evaluating, because I've got a lot of compiler optimization happening in the meantime.
Oh, like compressing, minifying, all that stuff?
Yeah, all of that kind of stuff. And even rewriting algorithms for me from the way that's easy for me to write into a way that's easy for the machine to execute.
Right.
The compiler will do that for me, and that's great. Again, why would I need to worry about these things? I'm interested in expressing my ideas.
Okay, you mentioned the compiler. I'm looking at my notes from the book, and I wrote down Haskell is statically typed, which means that when you compile your program, the compiler knows which piece of code is a number, which is a string, and so on. What is the difference between statically typed, strong typed? Is that the same thing?
The jargon around this is nothing like precise.
Okay, so it's imprecise.
So strong typing and weak typing, it's just down to whether I like it or not, essentially. So
it's not what, because like in this book, again going back to 7 languages in 7 weeks, like it would start the first sentence about each language, like blah 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 is a dynamically typed blah blah, like it would put all these words, and it sounded like it's very clear cut, and I was supposed to put it exactly in the coordinates of like this is exactly where it fits in the table. I will not understand. And it seems like it's not as clear cut.
No, it's nothing like as clear cut as that. But in Haskell, which does have this sort of misusing or sort of, bad wording, it's strong type. So everything in Haskell has a type. Okay, and worrying about types is a quite characteristic thing of how Haskell works and the Haskell community, the Haskell approach of doing things. So the idea is that you encode a lot of knowledge about the domain in the type system to the extent that it's sort of what you're trying to get to is the fact that if your program compiles, that shows it's correct. Whereas things like JavaScript and Python and Ruby and stuff like that, because they don't have those strong guarantees, you have to write lots of tests for it just to make sure all the bits of your program connect together and you're passing the right data from one part to the next. Whereas with Haskell, because the typing is very strict, I know all that at compile time. I know if these things are going to fit together properly at compile time.
So meaning that I have to define the type always, or can it infer it as well?
Both. So where it's useful, I will define types. Where it's useful, I will annotate functions with their type and values with their type. But again, Haskell is really, really good at inferring the types of things as it's going along. So, I know that part is an integer, and I know that's a string, and I know you're combining them that way, so I know the type of that is going to be. So it can work all that out for itself. But then in terms of the engineering side, it becomes useful to annotate what you think the types are everywhere, so that then if you and the compiler disagree, you find out quite fast. And then you can work out what's gone wrong. As opposed to leaving it to runtime when some things don't. You're expecting a set of numbers and you get a set of strings. And then things go wrong at runtime. It's much better if you know that at compile time when you can actually sort it out.
And is it quick to compile?
Varies. Because it's heavily optimized, there is a bit of a lag sometimes to get your stuff to compile, but it's not horrendous.
So Attila wrote regarding he said, I think regarding the asynchronous stuff, effectual operations like a network request are not just normal functions, they have to eventually run in I/O.
Yeah.
I don't know what that means.
I was hoping to avoid that kind of detail.
Okay. Okay.
But the point is, because I know that there is a function that's, say, making a network request, because I know it's talking to the outside world, then to make the Haskell compiler says this is dealing with the outside world where things may or may not happen.
Right.
And when I was talking about, I can put the bits with updating state and things are inside a little box where I can keep them contained.
Yeah.
That's what the IO monad is about. Is where I say everything's dealing with the outside world sits in here. And I have to, if I'm dealing with this, I have to worry about what's going on in the outside world. Outside that context, everything else is a pure function, and I can just do what I want, and I haven't got to worry about dealing with the messiness of the world.
Oh, but now you said the word, Neil. You said monad.
Yeah.
which is like a special word, I think, because it's so what I've been told about monads is do not worry about them because you will not understand them, or people explaining them to me in a way that's like, you didn't explain that to me. So, okay, would it be beneficial for us to talk about monads, or is it like, why is there this, I don't know, it's like almost like an inside joke that like, oh, wait until you get to monads, like what?
So monads are nothing like complicated if you come at it from the right direction. But there's a few things you need to understand to get there. So now I kind of have a plan of how I can get there in this, but given this is going to be an hour, I can't do it in 15 minutes.
18? I can give you 25. we can do like, and that is why, and then like we cut off, okay?
Yeah.
And I just do to be continued. And then we do previously, and then no, let's can you sketch it out a bit?
Okay. Right. So Haskell has something called type classes.
Type classes.
Have you heard of that idea, type classes?
No. Let's.
Okay,
yes.
So that's a good place to start. So if we can see here, I'm defining a tree.
Yes.
So like a binary search tree. Okay. Yep.
Yes.
So here is a new type of data, which I'm calling a tree. And it's a tree that contains some value. So it's a tree of things.
Okay.
But at the moment, I don't know what those things are.
Okay.
Okay. So I'm rather than saying the types, I could say it's a tree of integers, or it's a tree of strings, or it's a tree of whatever. But because I want this to be
miscellaneous,
polymorphic, I want to be able to store anything. I'll just call that an A at the minute.
Like a soup. Okay? Yes.
Yep. So this is what I say. So I'm saying a tree is either a leaf or it's a branch which contains a thing and it has a left tree and a right tree.
Okay.
Okay, it's a binary tree.
It's a binary tree.
It's a binary tree. And that's it. Okay?
It's a binary tree and that's it. Okay, but there's like lots of other words, but I will get it's a binary tree. Okay, continue.
Okay, so so this deriving bit, it just says, and Haskell knows how to sort of default implementations for how to check if two trees are the same.
Okay, equal, order.
How to compare trees, which is the ordering thing, and how to write trees out.
Okay.
So Haskell knows about how to do these things, and I might say, use the default for how to work that out, because I don't want to do anything clever.
Okay.
So that's what that divided is. Okay?
Okay.
You happy with that?
Yes. There's just like
Okay.
there's popcorn emoji, Neil. Like people are entertained.
And here's a couple I defined earlier.
Yes.
Yep. So I can do it here. Here is a string tree, and as I'm faffing around, I've got this bit, which is pretty printing them. So that's a prettier version of what it looks like.
Okay.
Okay. And there's a tree with integers in it.
Okay.
Okay, it's a different tree. And I can ask for the what type is that? Oh, it's a tree of strings. Okay.
A string tree is a tree of strings. Yes, makes sense.
It's not complicated. But then the question is, what can I do with this tree? What can I do with it? I can do. We've already seen I can do things with lists. Okay, so we've done list comprehension.
Yes.
But I can also use a function called fmap.
Oh, like a map. Okay.
Yeah. Okay.
So it concatenates this thing to every item. Oh, mapping over the array of
mapping
names.
over the list. Yeah. Okay. So it would be kind of cool if I could do that to this tree, wouldn't it? And if I could apply a function to all the nodes in a tree.
So fmap can be ran not just on lists, like on other types as well? Question?
That's where type classes come in.
Okay.
Yes. So there is a type class called functor. And don't ask me why it's called functor. I have no idea.
Because it's
I'm sure
fun.
It makes sense to someone at some point.
Fun factor. It has a fun factor of high.
Yeah.
Functor.
So a functor is a type class for containers, essentially. So a list is a container of things.
Yes.
Yeah. And this tree is a container of things.
Yes.
And something I can always do to a container of things is do something to each of the things inside the container and give me back a new container, which is necessarily the same shape of the old one, but has the things happened to it. So I can also do so I named a list of 3 items.
Yeah.
I find the length of each of those items. I get back a list of 3 items.
Yes.
Okay. Right. So, and because I want to say I can do this similar sort of thing with a tree, I'm saying that tree is an instance of functor.
Okay, so saying tree is a container of things.
Container of things. But to back that up, I've got to tell it how to do something to each of the things in the tree.
Okay.
So I say, and for trees, whenever I call fmap,
I
actually call map tree.
Yeah.
And this map tree is so this is saying I get a function and a tree, and I produce another tree, and this is how I do the details.
So it's kind of like a symlink, like a linking.
Yes.
Yeah. So in the context of tree, when I say map tree, I mean map through my tree. Okay, makes sense. So fmap.
So now I can, because I defined that, I can apply fmap to trees.
Yeah. So it's kind of like repurposing fmap for our data type.
Exactly.
Okay.
And I've got a tree of integers. I can multiply all the numbers by 5.
Right.
Okay. Yep.
You're right.
That's easy, isn't it?
Because now you have the fmap. You can map and do stuff to the items. Yeah.
Yes. Yeah. So that's the idea. but I'm capturing this general behavior of it's a container and I can do things to the contained items and put them in a new container. And that's what the functor type class captures.
Okay.
Yeah. And so
I was kind of hoping that you would say, and that is what a monad is, but no.
No, we get it. So get the idea of a
okay, functor, I get it.
The type class. There's another type class called foldable.
Of course there is.
Of course there is, which is about collapsing things together.
Yeah, kind of like reduce, no?
Pardon?
Kind of like reduce, like a reducer.
Exactly.
Yeah.
Yeah. Slightly more powerful, but it is exactly the same as reduce.
Yeah.
So, so what can I do? So that will combine all those things in the names just by concatenating the strings.
Right.
Yep.
Yeah.
And I can do the same thing on that tree.
Yeah.
Yep. And then I can start doing things like I can combine them together because I can't see where the bits are in between. So
so you're first mapping, adding that, and then you are reducing that.
Yeah. Okay.
Right.
Now, so the nice thing is you'll notice the only thing I defined was a function called foldmap.
Yeah.
I didn't define this one called foldr1. Because Haskell knows enough about type classes. If I tell it a little bit about how to do it, it will work out the rest itself. So if I do, so there's a function called sum, which adds up a list of numbers. So that's the total length of all the things in the list of names.
What's with a $sign?
It just saves me typing the brackets.
Okay.
This is a way of stringing functions together.
Okay.
So I can add up all the numbers in that tree of integers because some requires that it's a foldable container with something numeric inside it. Then I can add it up, and int_tree fits that description.
Oh, so you kind of hint at it, like you say, I've got this ingredient. And then it knows to make pad thai out of it. Like it knows if you give it noodles and this and this and that, it's like, oh, you want me to do this. Like it kind of fills in the gap. Okay.
Yeah, and so for the example, I can say, I know about how to make pad thai out of things. Chicken is a pad thai ingredient.
Could be.
Or fish is a pad thai ingredient.
As well.
And all I do is tell it how to do things like how to open the packet or whatever, and it can do the rest, take the rest of it itself. Yes?
Huh.
Okay, and so a monad is just another one of these type classes.
Huh?
But it's a type class which is used for combining functions.
Okay, we were doing so well. So, so it's
Have we got a bit of time?
Yeah, 6 minutes. So.
Okay. So.
It's another type class. Okay, yeah.
So let's say, actually, having 5 minutes. It's going to take more than 5 minutes.
Okay, I can give you 7. No, as long as you want. Just
it's
do it.
probably going to take about 15 minutes
Okay,
or so
I have
to go
15
through
minutes.
this properly.
Let's do it.
Okay, we're going to do it. Right. So, let's say I run a mail order online store or something.
Okay.
Yeah. And customers order things and I send the packages to them. And of course, customers always moan about how much postage is going to be, and they want to know what it is up front. Okay?
Right.
Yep, got that. So what I can define at this point is I'm going to write some code which does that calculation.
Okay.
Okay, so I'll define some types. So these are synonyms for things just to make life a bit easier.
So name. So key is what is that?
Key is like the primary key identifier.
Oh, okay. Address.
Yep.
Cost. Okay.
Yeah. And I have somewhere a wonderful database that has all this data about names and identifiers and addresses and postage costs and things. And for the purpose of this exercise, I'll just ignore that and just say, I'll take a name and I'll add whatever's key onto it. Just to pretend this is a database lookup.
Okay. And so the cost only depends on the location. The weight is always the same. Like you always get the same amount of glitter, let's say. Yeah. If you're selling glitter.
Yeah. So I've got these three functions.
Okay.
I can take a key from someone's name. I can take an address from their key. I can find a postage cost from their address.
Right.
Yep, happy with that. And that all will work fine. So let's just try reloading that. So that gives me, what's the key from the name? And it just does what it does.
Okay, because it's just, yeah.
Yeah. Okay, so the functions do what they do.
Yeah.
Right. Okay. But rather than trying to string these together manually all the time, I want to use these parts to make one big function.
Okay.
Which, if I plug in a name, it will spit out the postage cost.
Right. Makes sense.
Okay. Yep. Because why should I be bothered to doing all this stuff by hand?
We are, after all, in the business of automating things, Neil.
Yeah. So this is how I get an address from a name. I'm composing these two functions. So the dot is function composition.
The dot is a function composition.
Yeah. So what this means is I'm creating a new function called address from name. And the definition of this is I will take key from name, apply that to its arguments, and whatever that spits out, I would apply address from key to that result, and then pass that out as the final result of address from name.
So the return of key from name is the input from address from key.
Yeah. And here's another one, which is just those three stages put together.
Right. So.
Yep. So. And so I can.
So sorry. Whenever you change the stuff in the editor, you have to reload. Like you typed main.
Yeah.
Okay, that's like compile it again.
Yeah, it's just refreshing. It's again, if you're doing stuff in JavaScript, if you make a change to the file and then you need to just reload it and refresh it.
Okay.
In the because how else does it know when it's something that looks valid?
Okay.
So just a type of key from name.
Right.
Which is takes a name into a key, and the type of address from name makes sense.
Yeah.
Yep.
Yeah.
And you'll know that Haskell worked that out for itself. I didn't tell it what type this function is. It worked it out.
Yeah.
And
Wait,
And post cost of name, I take the name, it gives me a cost.
so
Okay?
so it worked it out.
Yep.
So you define this address from name, which takes two functions.
Mm-hmm.
But so how did it know? So when you define functions, it doesn't always make
Yep.
that function its own type, I assume. Like, how does it know when to make a type out of a definition?
Everything in Haskell has a type at all times. That includes functions. Functions have types.
So
the type of a function is something, so the type of post cost from name is this type is a function that takes a name and produces a cost.
So it's like a function definition.
Yes.
That's the same? Type and definition is the same?
No, the function definition is what it does. The type definition is what its inputs and outputs look like.
Okay.
So if you're writing a function, does JavaScript do type annotations and things? I'm not sure it does. Or is that pure script or TypeScript?
TypeScript
does.
Yeah.
You can specify the types of a parameter's inputs and the type of whatever it returns.
Yeah.
That's what the type of that function is.
Okay. Yeah. Okay. Mm-hmm.
Yep. So I've got these functions that they do things that I want them to.
So address.
Okay.
Yeah.
So you can see that they put together and they work and they do things.
So address from name takes address from name Eva takes Eva's key. Eva. So from Eva takes Eva's key. No.
Yeah.
Address from key. Okay, key from name. So Eva's key is address.
Yes.
Nice.
Mm-hmm. Okay. So this is so far so fairly simple.
Right.
You can see how this works.
Yeah.
Happy with all this.
I mean, simple, I don't know. But let's say we're following.
Yeah, okay. The problem is all these things are simulating database lookups.
Yes.
Okay. They may fail. I may be looking up a customer who's not registered and so nothing happens, nothing gets returned. How do I cope with that? That's a rhetorical question. The answer is there is a type. There's another container around called maybe.
Oh.
I can wrap things in a maybe.
Oh, like a try and catch type of thing.
Yeah, but it's sort of it's a level of values. So what should this function return? I'll produce this. So maybe I'll get a key from a name.
Right.
Okay, and it'll accept a name, and it may return a key.
Right.
Okay, and because I've got such a wonderful comprehensive database, if the name is Neil, it will return Neil's key, and for everybody else, it will return nothing.
I mean, that sounds a little bit self-centered, but okay.
Of course, but that's the idea.
Right.
Is that sometimes it will return the key, sometimes it will return nothing.
Okay.
Yep.
Yes.
Happy with that. Because these also database lookups, I can also define these other functions.
There may be, yes.
That will take a key and maybe return an address, and one which will take an address and maybe return a cost. Because again, all these database lookups may fail. What
is the just doing?
It's saying I have found it. So in this case, if I find the person name in a database, I return just the name. Or I return nothing.
And the rest? They don't have
the rest of what? So in these other cases, I couldn't be bothered to work out logic for when it would or would not return. So they always return. They always succeed. Those lookups always work.
Okay. So it's
even though
got it.
If it was a proper database lookup, maybe they'd fail and things.
Yeah.
Okay. So that's that. I can reload it and it all loads and it compiles, and that's fine. Okay. The problem is if I want to combine these functions. Okay. Can you see the problem?
Yeah, like the other one will run, but maybe nothing will be returned from the previous one.
Yeah. And also the types don't match. So the compiler knows there's a problem because the types don't match. If I want to string the output of this function into the input of this one, but the output of this one is a maybe key, and the input of this one is just a key. There's no maybe involved here. So I can't just do this function composition as I did here.
Right.
Because the return type of key from name, or maybe key from name, is not the same as the input type of address from key.
Yeah, and that is dirty.
Yeah. So I can't rely on function composition to do it. So I've got to do it long-handed. So I want to maybe address from key. No, maybe address from name. Give it a name, and that is maybe key from name. And so, no, not officially. Okay. So what this means is, if I want to find an address from a name, then I will try to look up the key in the database, and depending on the result, if it's just a key, then I'll look up the address from that key. If the result of this lookup of the name is nothing, then I'll return nothing, because there's nothing to return. Okay.
So you're kind of specifying, like the output is that, like in this case, if the output is this, do that. Okay. Okay.
Yep. Okay. But if I want to do this for these three things putting together, then I've got to start doing that. So maybe post cost from name, and I give it a name, and so it's a case
maybe address
key from name of, and just key. Right. And I can carry on and produce all this stuff, and the function is it's boring, isn't it? Watching me type.
As in, you have to cover all the different cases.
I've got to cover all the cases. And so I'll end up with a function that looks like this. So if the key from name gives me the key, then I'll look up the address. And if that gives me an address, then I can calculate the cost of it.
Yeah.
But if the looking up the address gives nothing, I return nothing. If the name returns nothing, I return nothing. And it's just, why am I writing all this rubbish?
It's not good. It does not look
it's
clever.
Not good.
No.
So, there's actually a better way of doing this.
Must be.
There must be. Right. You don't sound convinced.
No. I have all the faith in the mathematicians in Glasgow that they have figured out a better way.
Okay, so let's just comment this out. So this version was nice because I could just compose these functions.
Yeah.
Yep.
Yes.
But because the types don't match, I can't do the composing in the same way. So I had to go through all this long-winded boilerplate rubbish, which I don't like typing.
Mm-hmm.
So let's fix function composition.
Oh.
Okay. So
this is like, this was the perfect moment for me to say, next time.
You can if you want.
No. Let's do it. Let's just do it.
Let's do it. Okay. So I'm going to compose two functions that you have as maybe values.
Yeah.
Yeah. So I take a function I'll call f and a function I'll call g, and I'll return the function which is the two stuck together, fg.
Yeah.
Yep.
Mm-hmm.
So compose maybe is a higher order function.
Mm-hmm.
It doesn't take values and return values. It takes functions and returns functions.
Mm-hmm.
Okay. So I'll start with this one. So this takes something. So this could take, say, a name and returns a maybe key. Okay.
Mm-hmm.
Which is this type. But I can parameterize that, so I'll just take something of, I don't really care what it is, because something of type A to maybe something of type B.
Okay.
So you work on different types.
But do we like, is it costly to write longer variable names, or like I, B, C, F?
It's convention.
Ah, okay.
If you, same way if you see I, J, K in most code, you know it's a loop control variable.
Uh-huh. Yeah.
So in Haskell, if you start seeing A, B, C, you know it's standing for types.
Okay. Okay. Cool.
Okay. So.
Okay. So we're just allowing for a different return type.
Yeah. So, but that overall structure, where I take a definite value and return maybe a result, that's the important part I'm doing. I'm composing things that do that.
Mm-hmm.
Let's a bit more space there. So that's the type I'm doing, which looks a bit complicated, but you can see where it came from.
Mm-hmm.
Yep.
Yeah. So the maybe bit.
Yes.
So how does it know?
Okay. Well, I'm about to tell it. I'm about to tell it. This is the shape of the inputs and outputs of it.
Yeah.
Now I'm going to tell it how to do it.
Okay. So this is like a skeleton of, this is the type. Okay.
Yeah. So compose maybe. It takes two functions, f and g. Yep.
Yeah.
Okay. And it returns a function that takes some value and returns a maybe value.
Yeah.
So I can kind of follow the same pattern as it was there. So if you come across anonymous functions and lambda expressions and things in other languages.
Yeah, is that like, what is
the stabby function thing in JavaScript? The
stabby function?
So in JavaScript, you define functions that look a bit sort of...
like an arrow function, you mean?
Yeah, arrow function, that's the word. Stabby arrow.
Stabby.
So it's something like...
Why is it stabby?
Equals.
Yeah.
Equals. That one.
Yes. But why is that stabby?
Yeah.
Okay, so the...
arrow functions.
So the slash thing just means it's an anonymous function?
Yeah, so this is an anonymous function as you define it in JavaScript.
Yeah.
That's the syntax for JavaScript defining anonymous functions. This is the syntax in Haskell for defining anonymous functions.
Ah, okay.
Okay, it's the same thing. So.
Oh yeah. So Noreen said it's a fat arrow function.
Fat arrow. That's the good word. Yeah.
I mean, stabby. Just arrow. Okay. So okay, case gx off.
Okay, so this bit is just following the same pattern as I had up here.
So
I've got these. So go ahead.
yeah, no, it's just I prefer when it's more verbose, like there's more words. This is just okay. So compose maybe takes two functions.
Yep.
And then it has an anonymous function.
Yeah, and it returns a function. This is its return value.
Yeah.
Which is a function.
Which is a function.
And what this function does is it takes this one parameter.
Yeah.
And it applies g to it.
Yes.
Yep. And if the result is just something, then it applies f to that internal result. And if the result of this is nothing, return nothing.
Right. So because it's first.
And that's what I wanted to do.
Because it's first is doing maybe key from name, so that's the G.
Yeah.
And if that returns a thing, a key, then we do the next bit.
Yeah.
And if it's nothing, we just give up. Yeah. Okay.
So I can now do.
So case G.
Maybe what I call it. Maybe address from name is maybe address from key.
Oh, right. I know this backtick thingy. This is just for like a syntactic sugar, like for readability, right?
Yeah. Yeah. But what it does is you can see that this now looks rather like this did. Apart from the names are different, but if I'm using a dot to compose functions, I'm using this to compose them.
So it's like a smarter function composition.
Yeah. And I can do the threefold one, which is so I can compose those three things together. Okay. So now I can do maybe address from name. And it returns just my address. And if I ask, because my wonderful store doesn't know about you, that returns nothing.
And then the next one?
Okay. If I spell it right.
So that's nothing, and then wow.
Okay.
It works.
And that's how it does. Right. There you go. That's monad's done.
So what of it is monad? What? As in monad, a monad is the fact that you can make function composition smart?
Yes. That's it.
Wow.
That's it. So remember we had that type class about a functor is a container, and I can apply functions that walk over a container and do things, and the foldable I can collapse values into one. So a monad is just saying I can take a bunch of functions that have these sort of embellished types, and I can compose them together.
Right.
And anything that I can define something along the lines of compose for will fit into that monad type class. And that means there's a whole bunch of other stuff in the same way that sum is a function that's already defined on foldables. There's a whole bunch of other functions that are already defined on doing clever things with monads that I just get for free.
Right. Because monads are just clever function composition. What a journey, Neil. What a journey. I think that was well explained.
So there you go. I know, and the way it's actually normally defined in Haskell, they use a different way of describing it to get to the same place, but this is an easier way of explaining it, I think. So that's it. That's all monads are.
I mean, that's all. I mean, it was still quite a journey, right? Like, it's still kind of.
It's still a bit of a journey, yeah.
Huh.
So yeah, we did monads from a standing start in half an hour. There you go. They can't be that complicated.
Ship it. We'll sell it as a DVD, Neil. Now that I know how to calculate postage costs, especially.
Yeah. Yeah. As long as your name's Neil. As long as you're posting it to me, you're fine. If you're posting it anywhere else, no.
Wow. Oh. No, it's like, it's one of those things that right now, because you walked me through it, it's like, yeah, okay, that makes sense. Right?
Yeah.
Makes sense. But it is very like it's hard. I mean, in this specific case, yeah, it makes sense. Like, to avoid all these data lookups, and also to account for a data lookup not be returning an invalid return.
Mm-hmm.
Right, it makes sense.
Yeah.
And this is how you should explain things, right? Like, explain it to me in postage costs. Instead of saying a monad is a wrapper thing that wraps something and returns something.
Yeah.
Like, that was excellent.
Well, you can see how it's kind of a wrapper.
Yeah, now I see it. Now I'm receptive to it being a wrapper. But
yeah.
You can't just say, oh, Mona, this really difficult thing that I don't expect you to understand is just a function wrapper.
Yeah. Yes. Which is not a helpful way of describing it. Yeah.
It is not. That was excellent.
Good. Thank you. Are there any other questions do we want to do, or is
do
it
we have
so brains leaked out of ears and it's time to call it a day?
We had so Attila has been very diligently answering people's questions, because I've been asking you
and correcting all my mistakes.
No. He's been helping, because there's been quite an active chat happening in the background.
So thank you, Attila.
Thank you, Attila. Yes.
Yeah.
But yeah, so if there's no other questions, there's been a couple of exploding head emojis. Attila said, "Great talk, Neil. Thanks." So coming from
thanks.
Attila,
yeah.
this is
high praise indeed.
Yeah. Yeah. Thank you, Attila, for helping out. Wow, I didn't expect that I would understand at the end, Neil. So this is good. Well, you're a good teacher.
Yeah.
I'm just Now I think I'm gonna go and print a T-shirt that will say, like, ask me about monads.
Yeah, because you now know what they are. I mean, some of the syntax for Haskell and things is a bit different, but the concept of it's just fancy function composition.
I call it smart function composition, as in you can kind of go like middleware and help it decide how to be smarter. Yeah.
And the nice thing is because there's lots of other things that work with this at the same time. So you can think about functions that log what they're doing in this. As doing this, and there's sort of thinking about sort of threading through context and bits. There's lots of ways you can do it, but the main thing is you've got this monad that glues things together, which means I can write stuff which is as simple as this rather than trying to write this all the time.
Yeah.
It makes my life easier. It just removes boilerplate. That's always a good thing.
Yeah. I mean, I would probably start with writing the first boilerplatey version.
Yes.
And then, because you need, I think you need to be able to, like, you need to understand the repetitiveness of it in order to abstract it correctly. Yeah,
exactly. So we couldn't have got to where we ended up if we hadn't gone through all of this stuff first.
Correct, yeah.
Yeah, so very often you have to do that as you're trying to understand what it is. But as you're going through that, because you know there's this pattern it may fit into, you can say, oh, actually, it fits into that monad pattern. now I just define that one little bit of it, and everything else falls into place, and I haven't got to worry about it because the machine does that for me.
I mean, I will be saying this all the time now. Well, actually, this fits into that monad pattern. Yeah, I think.
Yeah.
Oh, awesome. Yeah, I think, yeah, I'm still amazed. Okay, can you stop sharing the screen so we say bye?
Yeah, I will stop sharing, yes. Okay. Sorry, yes.
This is exploding head emoji. No, it was good. It was really good. You should write a book, about
oh God, no. Yeah.
postage
Well, we
costs.
didn't even get to the really head exploding bit.
There's more.
Next time.
Yeah, next time for teaser trailer.
Next time.
Noreen did say that we need like 10 more episodes of Haskell. But I'll pitch it to Neil. No, we'll see.
Ask the boss if you can do it,
No, this was really good. Yeah. Okay.
Yeah. I think you're right. It is because it's different, because it's a different way of thinking about it. It can be hard work to get the ideas, but you get there. They're not difficult ideas. They're just unfamiliar.
And it's very. When I was reading about Haskell, it sounds, and it is like I wouldn't necessarily advise it to beginners, just because you need to have a little bit of experience to understand how it's different and why is it written like this. Like I think you can understand the benefits of Haskell when you are able to compare it to something else.
So there's two things going on. One is Haskell, the language, and one is functional programming, the approach.
Right. But Haskell as taking the functional programming into its most extreme, purest.
But you can quite easily start with functional programming as a starting place for understanding programming and machines and expressing ideas and things like that. But bits of Haskell, like type classes and monads and that kind of stuff, are definitely not the concepts you want to be doing as beginners. But you can start off with just the base. The first bit we did of just appending strings and all that kind of stuff. You can do that as a very beginner part of things. So there's nothing inherently difficult with functional programming.
Yeah, but it's very. Like it's very easy to write hello world, and it's easy to do a conditional or a for loop, but it's difficult to go from there. Like a lot of tutorials just cover that, and then like now you know enough, go and fly. But it's to be able to like but how can I use this? And like today what we did is like that's quite clever and that's a good use case for it, right? You could have a tiny Haskell like it doesn't have to be a huge thing, but like a utility thing, right? That you can say, I wrote this in Haskell, I learned something about Haskell and functional programming along the way, and it's a neat way of writing this down. So that is that difficult to get to from tutorial of hello world to like, now go and write. Because
there's a great site online called Learn You a Haskell for Great Good.
Okay.
Which is really easy to follow. Great tutorial. If you want to actually understand a lot of what's going on, that's a great place to start.
LearnYourHaskell.com. Oh yeah, that is it's the one that I had it bookmarked as well. I'll just paste it in the.
And that takes you through actually some quite advanced concepts, but nice and gently. It leads you up to them. I use it quite a lot still, so it's.
I was reading it, but it was like I stopped because the list comprehension was so long, the chapter. And I was like, oh, you can do this and that and that, and like by the time I finished list comprehension and I saw that there was like 20 more chapters.
It does have to do a lot of detail. List comprehensions can be very powerful.
Yeah, no, that's why
stuff you can do with them.
Yeah, and I found it very clever. Yeah. Yes, just a lot.
Yes.
Okay, cool. With that,
good.
Thank you, Neil. It was a pleasure.
Okay.
You did excellent work. I commend you.
Right. Good.
Yes.
Thank you. Have we stopped now?
No, I will.
Yeah.
I will say bye to everyone. Thank you
Yes.
to Attila again. And I am not sure yet about my next stream, but I will keep you all posted. Bye.
Yeah. Okay.